Yeah, so we are at week 2. I'm going to go ahead and drop the link for this week's slides into our chat. So one note is that next week we will be starting to really dive into StyleGAN. So this week we're going to do another dataset sort of tutorial. So next week we will be actually doing some stuff with StyleGAN. So if you've yet to train a model or if you want to train a new model, this week might be your week. So, give that a quick run. Also, I'll say we're going to use the PyTorch model in this class. If you haven't trained with the PyTorch model before, it's easy to convert your TensorFlow models into PyTorch. There's a script that I'll link everyone to. But I would also recommend I'll link to the video from the last class I taught on how to actually do training in PyTorch. If you've only ever done the TensorFlow version, it's kind of annoying because you have to like convert all your images to these TF records files, which are enormous. It's very painful. The PyTorch version eliminates that. It also trains about 25% faster. So you'll get way more mileage out of your collab sessions or whatever. So I definitely recommend checking that out. So I'll link to that video for anyone interested in that process. Otherwise, it's pretty much the same as training a TensorFlow version. You set up some of the particular arguments, you point it toward a zip instead of your TF records folder, and you let it run, and it just runs for a while. So I'll link to that just so people have that. But yeah, next week we'll start doing some more StyleGAN focused stuff. But if you don't get to finish training, you can always play with sort of the models you have. I can also link people to pre-trained models if they're interested in using those. Yeah, so I think we'll dig into more of that next week, and I think it'll be pretty fun to get started with all of those tools. One other note is so I think if you've taken any of my previous classes, you'll know that I usually sort of hide the code a little bit inside of scripts or like Python scripts that you can then just run from the command line with one line. For this class, I'm actually going to try doing a little bit more code directly in collab cells. So what I think that means is for those of you who are interested in the code, you'll be able to see it a little bit easier. For those of you who are less interested in the code, it might be a little bit more confusing. But what I'll say is just sort of glaze over the rest of the code and just focus on where I make edits to things. And I'm always happy to help where I can with sort of okay, I don't remember what I'm supposed to edit in this cell and what I'm not. But the hope is just I also want people to get a little more comfortable with seeing code in cells and maybe being able to sort of I do this quite frequently. I sort of glaze over the code and I look for stuff that looks editable or that it points to a path or that sort of thing and edit from there. So because as you get further and further into machine learning, you'll find more and more people just dumping huge chunks of code into their collab files. And that can feel daunting at first. But I want to sort of help everyone get a little bit less scared of that experience and maybe sort of help break down where things are editable. What does Python usually look like? What do you normally need to look for to edit things, that sort of thing. So we'll start with some of that today. And then we'll definitely be digging into that more over the next couple weeks as we edit directly inside of StyleGAN notebooks. Yeah, I'm not sharing my screen yet. Thank you. I appreciate that because last week I messed it up so many times. So I really appreciate people reminding me that. So as I mentioned, this week we are going to look at some more data set materials. So we're going to look at two tools. One is called LPIPS and one is called CLIP. Many of you have probably already heard of CLIP because it's sort of all the current rage in the machine learning image making sort of world. We're going to use CLIP a little bit differently today, and I'll talk about what that means and what that is. But you've probably seen lots of CLIP generated images, and I might touch a little bit on that when we get to it. So next week we will jump into actually using StyleGAN. So we'll actually look at what the latent space actually looks like in our code, how to manipulate it, those sort of things. And I might actually move feature vectors up to next week. I'll sort of see how far along we get in terms of material. I would like to start maybe if I can squeeze some of this stuff together because I think there's some new things or things I didn't really cover here that I'd like to cover in this class if I can. So we'll see. We'll see how it goes. And you're always welcome to give me feedback if you feel like we're rushing things too much. And one note is, so I did take a look at the survey. So we'll be doing co-working sessions. I picked two times that I felt like had the largest sort of Venn diagram of people being able to show up. So we'll be doing one at Saturdays at 2 p.m. These are all Eastern Standard Time, so Brooklyn, East Coast, New York, or East Coast America. One note about this one is I have a class that goes from 12 to 2. So depending on if that class runs briefly over, I may be like 5 minutes later so to that session. But we'll usually do these for about an hour, and I find people just show up when they show up and like can check out whenever they're ready. And then the other one will be up Mondays at 8 p.m. So I tried to make this work for everybody. I don't think it worked for everyone. If these are times that don't work for you and you want help, just DM me, and I'm always happy to set up extra time outside of these times. But I felt like this would be the most flexible just for everyone that could attend. I'll send out a calendar invite, and then if you've never taken part in my classes before, usually what I'll do is in Slack the day of, a couple hours before, I'll just drop a note and say like, hey, I'm going to be doing a co-working session. If you want to attend, like you just answer with an emoji. That way, if no one is planning on attending, I know, and then we can just skip it. So reminder, these are optional. I find them helpful. You can ask sort of pretty much anything. I find that we never really have more than 3 or 4 people in there, so we've always got time to cover everyone's materials. And they are sort of helpful. It's like nice to sort of hear what other people are working on and maybe answer some questions that way. So even if you don't have questions, you might want to show up and just sort of like learn by osmosis or just sort of soak stuff in. So I'll send out invites for that probably tomorrow, and then Saturday we'll do our first one. Okay, so I want to jump into talking a little bit about data sets and dataset diversity. Mackenzie or Yugasa, did we cover this in our last class, LPIPS at all? Okay, yeah, I didn't think we did, so I thought I'd cover this here. I've taught this a little bit more in like I taught a class at ITP earlier this year, so I taught a little bit of this, but I think it's an interesting tool, and I think it's helpful to sort of think about how machines think about your data sets in regards to diversity. So you will often hear me talk about diversity in terms of data sets. And the way I sort of think about that is how different are your images from each other. So again, talking about alignment from last week, alignment is, finding a place where your images sort of like have a similar structure, or finding a place where they can sort of align. Diversity could play into that, but also like diversity is about just how different each image is from each other. So you can sort of think about these as sort of onion skins, right? Where like maybe there's something aligned in the middle, but like beyond that, like stuff can shift a little bit left or right, right? But if things are really different, like that could be considered like really diverse. Or if they're like completely different materials, right? Like you've got a painting, an abstract painting in one place, and then like an animal face in another. Like those are so different that like, a machine learning model, especially like StyleGAN, is going to struggle to sort of figure out how to match those two together. So diversity is important in that you don't want things too similar, right? I think some of you have probably tried stuff with like taking every single frame of a video and feeding that through a StyleGAN model. And what you find is that it sort of memorizes things because the frames are too similar. So you do need a certain level of diversity so that the model can figure out how to train different things and mold that latent space. So diversity is like one of these things where it's like, you don't want the exact same image, but you want them close enough. And one of the challenges is like, well, what's close? Like, how does a machine think about close? So we're going to look at a tool that sort of helps us in some ways to look at that, and maybe doesn't in other places. And I'll cover that in a minute. So you're probably sick of seeing these people. This is the StyleGAN dataset. We talked a little bit about how they're aligned, but you can also look at how they're similar or different, right? So the diversity of this data set is you've got people with hats, you've got people with different skin tones, different lighting, but you also have sort of different facial directions, right? Like this person is sort of looking down and maybe to the left, and this person is sort of looking maybe up a little bit and to the left, but the face is sort of turned a little bit, maybe 30 degrees versus this image here being straight on. So there's still a decent amount of diversity in these images, right? And you've got different background colors, you've got different hair colors. So there still is a lot of diversity in this data set. And I think it helps that they've got 70,000 of these images to use. That is like a huge number. That's a huge image data set. But within each of these, there's also a lot of diversity. So here's sort of an interesting place where some things align, some things are similar, but a lot of stuff is still very different. So, I think in an ideal world, all of our data would look like this, and the truth is not all of our data does. But sort of one of the challenges with machine learning as a whole is just what makes a good data set. These are images that I traditionally train on, right? And you can sort of see like, well, how similar are these? Like, they've got similar colored backgrounds. They've got flowers of similar colors. They've got leaf shapes of different colors. But like, if you were to onion skin these things, they don't really overlap in any places. So how do we determine like what's good enough or what's diverse enough or like what works? And I will say like from a research standpoint, a lot of researchers are trying to figure this out too, because in an ideal world, you would just scrape a whole ton of data and just throw it at the model. But if all the data is set up differently and too diverse, that can cause model collapse. Or it could, maybe there's ways to take a third of that data and group it into one category and train on that. And of course, like machine learning researchers never want to do anything by hand. So they're always looking for ways to automate this stuff. And like, well, I think as artists, it's good to have some handmade craft in our work. I think it also would help us to know like, okay, but could I just use this smaller data set and like have a good model trained of it, right? Because training takes time. So everything people want to do is like, how do I reduce the time to train? How do I make sure that I don't have issues? Then I have to retrain again, that sort of thing. So I don't think we've talked about horse to zebra in this class yet, but horse to zebra is one of my favorite data sets because it was used for the StyleGAN model that generates horse to zebras. So it literally can convert a horse to a zebra. So these are the images directly out of that data set. And if you've seen, the StyleGAN model from maybe 3 years ago, 4 years ago, wasn't the best, right? It was like, you could tell it was a machine doing it, but it's still fascinating. And when you look at the data, this being the data for it, you're like, wow, it's amazing that I was able to train that well off of these really crappy images, right? There's no alignment here. There's like very little like structural similarities. You've got people in some of these images. You've got boats in some of these images, and yet it's still able to do translation. Now, one of the reasons for that is because translation networks work a little bit differently than a StyleGAN network does. But still, like, here's a data set where, again, some machine learning researchers grabbed about 1,000 images of horses and 1,000 images of zebras, threw it at this model, and it worked. How could we get more like that, or what can we learn from this to sort of take a look at this data a little bit more? So as I mentioned before, like we do need a balance, right? We need some balance of diversity because we want the model to learn different things, right? If it memorizes everything we give it to it, it's almost like we didn't have to do any work. We could have just like done that by hand by just repeating our own images back to us. So we do want the model to quote unquote learn something, and that comes through diversity. But generalizability is still really important. And I think one of the things that's sort of fascinating about this area of research is that I think humans have sort of an innate or like, a very like biomechanical machine learning person would talk about, well, like your brain also is a series of machine learning nodes that can break things down very simply and then learn what matches and what doesn't. But machines think differently, or like it's less hidden than a human brain, or like how quickly a human brain can sort of work. But we do want to sort of think like, okay, well, how does a machine look at these things, and how does a machine determine what diversity is or isn't? So that brings me to this tool called LPIPS. LPIPS, I think, came out in 2018. So it's actually a fairly old tool, and I'm kind of surprised that no one's really come up with new things since then. I did a little bit of research and didn't really find much else that's new. But LPIPS is a tool that essentially tries to measure the difference between images. And there's lots of ways to do differencing, right? You could do it directly in Photoshop, right? You overlay two images with each other and you use the difference filter, and it gives you sort of like the edges or like the color of things that are different. You could do the same thing in NumPy. You could literally subtract the image values from another image, and you'll get some values there. The problem with that is that's on a pixel by pixel basis, and what we really want is structural, right? We want more than just pixels, because say you take a photo of me in red light and a photo of me in blue light, if you difference those, they're gonna, and it's the exact same photo, like they're gonna to in that sort of like coding environment, it's going to look very different because the color pixels are different. But the reality is the structures and the way my face looks shouldn't change. So what LPIPS tries to do is like, how do we actually determine difference on a structural level? And that happens to be something that machine learning and deep learning is very good at. So what it does, it uses activations of a network called VGG. You've probably heard VGG before because it's used for style transfer, it's used for other things. It was one of the big sort of classic deep learning models of probably 5 or 6 years ago, maybe a little bit longer. So it uses those layers. And if you remember, like the way deep learning works is that there's a series of layers in a machine or in a model, and that the earliest layers are very structural, right? They're like, what is the outline or the shape of this thing? And as you get deeper and deeper into that layer, into those layers, you get finer and finer details, right? Like what's the texture of my hair, or what is the coloration of this patch of my beard or whatever it is. So they use that model to actually sort of determine how two images are activated in a similar way. So let's take a look at this really quickly. Actually, so before this, I've got 3 images here. So with the image on the left, which of the 2 images, this one or this one, do we think is closest to this? You can just shout it out if you want to.
One with the pool.
Want the pool? Okay.
Yeah, right.
And why would you say it's the one with the pool?
Because the zebra's like basically in the same pose and like sort of looks kind of similar. Slightly smaller though.
Yeah. So that's right. I have to say when I first looked at this, I thought, well, for sure it's like this image, right? Because these people are here, right? And there's no people in this image. This one is smaller, it's in a different location. But yeah, Dusk, you're absolutely right. So LPIPS actually scores these like this. So LPIPS provides a distance score. So it takes 2 images of the same size, and that's really important. They have to be of the same size. And it then compares the 2 as it's activated through a certain neural network. And then it provides a score. Now you'll see here, the score of this image is 0.796, and the score of this image is 0.869. So the model says like these are still pretty far apart from this image, but this one is closer. And I think it's almost surely because the pose is the same, it's just flipped left to right, whereas this is like zoomed in, cropped, that sort of thing. So one of the challenges here is like how much of a distance score is a good score or bad score. And that's something that I still don't really have a good handle on, but we can use this tool to begin to see like how close are our images to each other. And I imagine like this is sort of like a rough way of thinking about how this would actually work. It takes in this image through the classification model, and it sort of like lights up certain neurons that it really like activates. So maybe this is the shape of a horse or shape of a horse / zebra sort of layer, and then this is like the the texture of the zebra, and then in between it's sort of like we've got legs in these certain poses. Maybe its neck is pointed down, that sort of thing. So then we'll compare that to this image. You'll sort of see like, okay, these activations don't align the same, whereas maybe with this one they do, but there's like 1 or 2 things off here. So this is what LPIPS does. LPIPS also adds they have another layer that is like an actual trained layer where they actually did supervised learning to say like these images are close to each other. So it's not just purely, I have a notebook on like doing like t-SNE, which is like literally just looking at the network layers. This is supposed to be a little bit improved from just purely network layers. Save a little bit of train layer on top. So the idea is this is better than even just like purely just running it through the activations. I can't say much more than that because it's a little bit over my head beyond there. So we'll look at how to use this in just a minute. I find LPIPS to be an interesting tool to remove very different images, right? So if you want something that's really far out there, this is a good tool for that. If you want to try to figure out like, what is this image's score compared to this image, it's helpful to like, you get a number, but you don't really know what that number represents, right? Like, should it be closer? Should it be further away? And the paper, which I think I linked to a couple slides before, does have some interesting sort of examples of, the way they do this is they shift an image to the left or they shift an image to the right, or they like zoom in, zoom out, and they sort of compare the scores there. So You could also do something like that with your own net model, just sort of like see how it compares. But I do find it's a little bit, it's a little bit of a guessing game. But you can sort of play with your own data and sort of see where it goes. One thing I will also note is you would assume, well, FFHQ trains so well that the LPIP scores must be really close. And what I actually find is they're not. I don't have the exact numbers in front of me, but I feel like I ran FFHQ on about maybe 1,000 of the 70,000 images. And I think the average score was around a 0.7, 0.75. So, again, if we go back to this, that's like this image and this image. So, that's helpful data to know because LPIP still trains well, or sorry, FFHQ still trains well, and maybe that's a good idea of what the score range should be. But that's not to say that so you might assume that LPIPS will say like, oh, well, if all these images are 0.5, you'll have a really good trained model. And I'm not sure it's the exact same thing that that's saying, right? So we use this as like sort of a way to sort of check out our data and look at things, but it's not like a foolproof system. I'll also say that they have 3 different models that you can use in the LPIPS model. So there's a model called AlexNet, which is GoogleNet. There's VGG, and there's SqueezeNet, which is more of a mobile network. And you can try testing scores with any of these. Some of them have better performance, and others have better speed optimizations. So I think in the paper it says AlexNet performs the best from their point of view, and SqueezeNet is the fastest but performs the worst. So if you have 100,000 images, running these tools might take a couple hours. So I would probably look at SqueezeNet first and see if it gives you good enough results compared to AlexNet, those sort of things. So we'll look at this in just a minute, but just know that there's some stuff to dig around in here. And I always recommend reading the papers, even if you don't know the math, you can at least sort of look at the diagrams. I find looking at the diagrams in papers is often the most helpful thing for me, because I'm at least able to sort of see okay, what are they doing here? Okay, I get that. And then I can maybe read the paper and understand a little bit more of it. And I should say, LPIPS isn't the only tool that can do this. I've previously mentioned tsne, which is another tool that sort of aligns stuff to grids or clusters. Now, again, this won't really tell you this cluster is better for training, but it will help you at least maybe sort of visualize where in these clusters a lot of your data is, right? So if 85% of your data is in this one cluster, you might just want to delete everything else or remove the images that look like that. And there's a bunch of tools. There's one called UMAP. There's PCA, which is another thing. We might cover PCA a little bit when we talk about vectors, because vectors are often built using PCA. But there are a bunch of tools, and I think this will link out to maybe one of them if you want to play with your own to just sort of see what it looks like. And this is still machine learning based, but there are other tools out there that are purely pixel based. So there's averaging, there's standard deviation, more mathematics sort of things. But these are still pretty common in data science. It turns out they don't work as well for machine learning and deep learning, but if you are interested in them, you can play with them. And also Pragmatal, who is he teaches at UCLA and their DMA program. He just put up a class, I would say maybe 4 or 5 months ago, that is a class all on sort of image statistics and other things. Is really cool. It is I think it's 8 videos and they're all 3 hours long. So it's a lot to slog through. But if you are interested, there's some really cool tools in there to sort of do image averaging and other things to sort of understand a little bit more about what's going on behind the scenes. And lastly, I always bring this up when we talk about scores because I feel like people obsess about scoring, right? They're like, oh, I have to get my score lower, or I have to get my images to be a lower score. And the truth is, it matters a little bit, but I don't think it matters as much as people think it does, right? So if you've got a couple images in your data set that are a distance of 0.9, I don't think it's really going to change your model that much. But if the average score of yours is 0.9, maybe then you've got a problem. So, use these as directional, not as a hardcore score that, I have to get an A on this test and therefore I must get all of my scoring to be a 0.5 or lower. I use all of this stuff as gestural. It's not set in stone that I need to do this in order to have a thing work. So, all right. So with that, let's take a look at LPIP. So let me grab the link to this and I'll drop it in our chat as well.
Derek, I have a quick question for you on the scoring idea.
Yeah.
Are you generally more concerned about bringing down the average overall or removing like large outliers that are like really outside the set?
I definitely look at outliers. Again, it depends on how many you have, right? If you've got a data set of 10,000 images and you've got 50 outliers, StyleGAN is going to throw those outliers out as well. So I do think it's helpful, but for a lot of us, we have 1,000 images, right? So if we have 1,000 images and 100 of those are outside of our score, that might actually influence StyleGAN in a way that we don't want it to. So for this, I'm going to actually like just throw out outliers. So we'll set like a minimum value and then we'll just like remove anything that is higher than that value. I don't have any tools here, but we certainly could think about like, if you're interested in building tools, one thing that would be really cool would be to think about like, can I shift an image or like zoom in on an image and would that change the score, right? So there's actually a lot of art projects that are sort of like, how do I manipulate a score by manipulating the image in order to get something closer to what is approximate. And that sort of maybe aligns with what we talked about last week, which is like, how do you align data better? My guess is that if you align data better, it will generally score better. That's actually kind of a guess. I don't know that for sure. Like actually what I should do is now that I've got that FFHQ in the wild data set, I should also do the scoring, an average score for that data set, an average score for FFHQ. That might also show us like how different these things are. So I will say like I've used this a little bit just to toss out like really wild variables. But in general, I'm hand querying a lot of my data, which is, just I think it's helpful to just be closer to the source. But I think it's an interesting tool and it's one worth playing with and exploring a little bit more. So that's a link to notebooks. We'll go ahead and open it in Colab. And I'm just going to switch my account here real quick and hopefully get a faster GPU. So with all these tools, I'm going to just do some really like toy data sets where there's like 20 images. That way we're not sitting here waiting for this stuff to render forever. But know that for most of these tools, like I'll throw 50,000 images at these things. I did one with the clip stuff that we'll look at in a little bit, where I did, I think, 25,000 images, and it was able to sort them in less than an hour. So this stuff can do a lot with like big data, which is really cool and really nice. Both LPIPS and Clip do like if you have a GPU. You can use LPIPS without a GPU, but it is slow. So, anything that's CPU related is like 10x slower, if not more. So I will generally do these on Colab because I have access to a GPU that way. Or I'll do it locally where I also have access to a GPU. So a GPU is very helpful for a lot of these tools. So let's just see if I get any, if I get a V100 or a P100. I feel like I've been only getting P100s this week, so it's the world we live in these days, I guess. Oh, I got a V100 for once. Okay, awesome. Not what I'm going to do training. That's a bummer. Anyway, so from there, all we're going to do is we're going to clone in the library that is its perceptual similarity. I forget exactly what this thing stands for, but LPIPS somewhere in there is the PS is for perceptual similarities. We'll go ahead and run this. Cool. I also think, oh, there is so there's also a Python plugin that is LPIPS. So for this, we're going to install the Python library, and then we're also going to use, there's some scripting tools built into the repo. So that's what we're going to use here. So next we'll need to get some data. You're welcome to use this for this sort of session, and then you can upload your own data. I'm actually just going to import horse to zebra. I think I just grabbed it off the StyleGAN website and moved it to my own drive. So we'll just download and unzip horse to zebra. And if you look inside horse to zebra, you'll see there's a horse folder and there's a zebra folder. And I think there's something like 1,000, 1,200 images in each of them. This is actually pulled from, I believe, ImageNet. So if you've ever played with ImageNet, these are just the two categories from ImageNet. So let's take a look at a couple of these images. So I just grabbed like 2 horses and 2 zebras, and we'll just display them in our session here. So you will see like these images are stretched in all sorts of weird ways. So we've got 2 horse images. We've got a horse butt. We've got a horse face. Looks like we've got some more zebra butts and a zebra face. So, again, the data set is pretty diverse here. So it'd be nice to sort of know like, okay, well, how do these images score comparatively? So there is a way to compare 2 images. And the way you do that is using the LPIPS underscore 2 images script. And then what you do is you pass it P0 and P1. And P0 is your first image and P1 is your next image. And then because we have access to a GPU, you want to make sure that we're using the GPU. So you use this flag to turn that on. It will definitely help make things go faster. So I highly recommend that if you could do that. And I believe the 2 images we're going to look at here, if I look up here real quick, is I think we're going to look at this horse image and I believe this zebra image. So I believe that they are both the faces. Let's make sure of that. 1001 and 1000. Yeah, so we're going to look at the 2 face images. And we're going to see how they compare. So we'll just go ahead and run this cell. And when the first time you run this, you also have to download VGG, or sorry, this is AlexNet. So by default, LPIPS uses AlexNet, which is what they say is the preferred version of what they find works the best, or the best performance. No, best accuracy. So this gave us back a distance score of 0.766. So that's kind of interesting because if we saw that other score with the full-bodied horses, this is only slightly lower than that score. I think that other one was like 0.796. This is only slightly better than this. And it's still like, I would say those 2 images, if we look back up here, this horse and this horse, like those are pretty close to each other, I would imagine. So again, the distance score, from my experience, tends to be higher than I expect it to be. And again, this is probably where if I really wanted to do more research in this, I might take an image and manipulate it, like zoom in, zoom out. What does that do to changing the score? Sliding pixels left or right, how does that change the score? So there's probably a lot to learn from this model. There's some good baselines on their website if you're interested in looking at it a little bit more, but I think pretty much with any research model, you could spend another week and like make some far cooler results than even the researchers did. So if you're interested in that, that might be some cool things to try this week. So that's the basics of just using this LPIPS library. Now inside of here, they have a couple other tools as well. There is a 2 directories. So I believe what 2 directories does is it does 2 pairs in a folder. So if you imagine like folder A is image 0 through 1000 and B is 01 through 1000, it's going to match up those numbers. So it's going to go 0, 0, 1, or sorry, 0, 1 and 0, 1, 0, 2 and 0, 2. So it's going to just try to sort those. So that is another tool you could look at if you have 2 data sets. Like you could run this with horse to zebra. I believe the tool would be something like this. Let's add a code layer here. So it'd be 2 DIRs instead of 2 images. And I believe, let's do, oh, that's going to throw an error. So you have D0 and D1. So it would be D0 is, D0 would be this path. And D1 would be the zebra path. So you could run this and it would show you all of the pairwise distances. The problem is that doesn't really make sense with this data set. It might make sense with something like a pix to pix data set where the stuff is perfectly aligned and you want to see the score between those 2. But they have it here if you want it. One dir all pairs. I do not remember what that does. So I would just, you can just sort of like dig into the repo and sort of see. What I've done actually besides this is I've actually implemented some of this stuff in my own dataset tools library. So we're going to look at that where I've built in some additional tools. So in this case, what all you'll do is you'll just clone down the dataset tools repo. And then I've got a command here that uses the sort script. So if you do the sort script and then you do, this stands for process type, so -p is process type. And then you can pass in the process type of LPIPS. So what this is going to do is it's going to, you give it a starting image, and then you give it a folder. So in this case, let's say I have one zebra image I really like, and I want to look at what that, like I want to find all the images that are closest to that zebra image, right? So that's what we're going to do here. So we're going to take one zebra image, which let me drop this in here and see what this looks like. So let's do display. So we will take this image path. It's warm here in Brooklyn today, and I can tell my laptop is struggling with both this and Zoom working. Come on. Nope, not working. All right. Why don't we do this? We're almost finished with this, so why don't we just take a quick 10-minute break? I will stick a fan on my machine and maybe stop and restart Zoom, and then we can come back and pick this up. So why don't we just take a 10-minute break? So let's come back at 8:30, and I'll hopefully cool this guy down, and then we can finish this out. So I'll see everyone at 30 minutes after. Kristen, I'll get to your question when I finish up the section, but that's a good question, and it's definitely like annoying. Caleb has some annoying details with that. Okay, so I think I've quit all of my applications. I've closed out the 50 tabs I have, and this seems to be running smoother, so fingers crossed. Okay, so where we left off is we were looking at what this image was. So it's this image. This doesn't even look like a zebra. It looks like a, like, what is it? What are those things? Tapirs? Looks like a straight tapir. I don't know. Anyway, this is the image that we're going to look at. So basically what we're going to do is we're going to compare every image in our folder to this image, and we're going to get the score. And what we're going to do is if the score is, oh, I'm not sharing my screen. Thank you. How? I swear to God, I hit that button. Okay, thank you again. Eventually I will get this in like week 7. So we are going to compare this guy to all of our images in the zebra folder. So, and then we're going to look at the score. So you'll see here there is a max distance. So basically anything that scores higher than this number is going to get thrown out. and anything that's lower than this number we're going to keep. So our input folder is all of our zebra images, and our output folder is a folder we're going to create called zebra sort. So when we run this, we will say starting image is going to start with this. Here is our max distance, and we're going to use the AlexNet. So you could also switch this out to VGG or Squeeze if you want to try those networks just to sort of compare scores. Alex is the one that they say works best, so I just tend to stick with that. And then we're going to use the use GPU, and then -v is for BOS. Basically what I want to do is I want to print out all my scores just so I can sort of quickly gloss over them and see what's here. So we'll run this cell. And that's how fast it runs. It runs really fast. So you'll see it's just dumping out a bunch of scores here. So if I go to the top of this output and I just sort of quickly scan through these, so I see a lot of 0.6s, 0.7s, a couple 0.8s, 0.81s, you know, so there are some higher scores in here, but for the most part, it looks like most of these images are about right. You know, there's a 0.95, which again, if you really want to explore, you could also like open this image and look and see what it is and see like, oh, how different are these? My guess is that a 0.7, 0.5, or 0.8 is probably a good starting value, just to sort of like begin to create a sort. So as you go through these, you'll just sort of see there's a bunch of different scores here. I just tend to keep an eye on them, just sort of be like, oh, I wonder what the average or what I'm sort of seeing by default is. I see a lot of 0.6 and a lot of 0.7, so that means, you know, again, this data set is probably like fairly well aligned, because I remember when I did FHQ is about the same, a little bit higher actually, I would say. I feel like I saw more 0.7s than I did 0.6s when I ran that. So this might be a thing where maybe you just want to download a bunch of data sets and just play with this and see what average scores you get with each of those, just to sort of compare them. So yeah, so this is, yeah, go for it.
So the max distance value in the input, what did that end up doing? Because I see scores above and below that number.
Yeah, so this outputs every score, but the actual folders are different. So basically, if this image is higher, it'll output here, but it won't show up in the zebra sort folder. And I'll show that in just a second. But yeah, that's a good question. Yeah, so this will just output all the scores, just so you know what they are. And then down here, so what I've done is, this is some quick code to just sort of count how many images are in a folder. So if we look at our original data set, there were 14,074 images in that original data set. And if we run this cell, we'll see that there are now 977. So it looks like actually about a third of my images were higher than that max distance score. So you know, I just sort of find this as an interesting tool to just sort of play with and sort of see, you know, what does my data set look like? What do other popular data sets look like? This is a case where maybe I want to run this on horses, and see what horses, like see if the horse data set is that different. If you're familiar with using like NumPy or something, you could probably very quickly get the mean score out of this as well, or the standard deviation of how different these scores are. Maybe that also tells us a little bit about this data. The truth is, like, I feel like not a lot of people have really researched what a good data set looks like from these sort of perspectives. That maybe we learn like StyleGAN works really well if the standard deviation is below 1 or whatever it is. So, you know, this is why I like teaching these classes, because hopefully some of you will jump on some of that or find some interesting details that then we can all use in these courses going forward. So that's sort of the basics of LPIPS. I do want to show one sort of like fun example that I've done with this, which is I made this video a couple months ago that actually takes all of these images from a data set I have and sorts them according to their LPIPS score. So I've got a bunch of other like shit going on in here, but you'll see there's sequences where there's just a bunch of fast repeating images. And all that is what I do is I start with one image, and then I go through an entire folder and I find the closest distance to that image, and I take that image. So that image is now 2. Then I take the second image and I go back through through the entire folder, find the closest image to that, and I take that. So now I've got 3. And I do that iteratively and iteratively and iteratively until I go through the entire data set. And what it essentially gives you is your data set ordered according to how LPIPS would score it. Now, if you look at these, you could probably say like, I kind of understand what LPIPS is looking at, but it's also just a little bit interesting and different. So I just did this as a way to sequence these images, but I think it's, again, it's another cool tool. One thing I will say is this is a very greedy process. It is very slow. I think to run it on the, like I had something like 6,000 images. I think it took about a day to run because it goes through every single image multiple times, then it like removes one from a folder, and it goes back through that. So it takes a long time to sort through this. But again, I think these are cool ways to begin to think about how you can build a data set or how you can sequence images in a really interesting way. So that script, if you're interested in it, is in, I have a forked version of the perceptual similarity. I'll drop this here. I have a forked version, and I believe it's the sort to sort. Of course, is a wonderful name for a file, but this will sort your images according to this. So if you're interested in playing around with this, I've got some other scripts in here that are sort of like, I'm also trying to do a thing where I'm sorting video. So it takes, finds the last sequence in a video and it finds the next frame in like a cut, essentially, to try to like recombine video. I've got some stuff that might do that. If it's not here yet, it will be in the next week or two. So I think there's, even within just LPIPS itself, there's cool ideas you can begin to explore with these things. So yeah, I think there's a lot of interesting stuff within LPIPS, and you know, it's been out for a couple of years now, and I feel like no one's really like jumped on it too much. So I think it's in an interesting place and is ripe for sort of some discovery. So yeah, play with it, see what your data set looks like, see what other data sets look like, and let the group know if you find any interesting detail that might say like, hey, this will probably improve my data. So, so Kristen, I want to get back to your question, which is, does Colab support pull requests? Yes and no. So when you clone one of these repos down, it is essentially a Git repo. And you can make edits by, like, say you want to double click into one of these files and just make an edit. You could do a Git push or submit that as a pull request. The downside is that none of your Git config stuff is saved here, and it gets really messy. Like there's some weirdness around it. So in general, I would say that the simplest way to do a pull request is just to like literally download it locally and make edits there. You probably can, but every time your runtime reconnects or resets, you lose all your Git config stuff. So you have to like upload it back up. So maybe you could have like that saved as a cell that you then like bring into various notebooks. But yeah, it is definitely a little weird. There's like, I find it a weird hiccups with Git, trying to do Git directly in Colab, but you could try it and see what happens.
Would the simplest thing you think for like what looks like a demo script just be to ping the author and be like, hey, this line here is missing and breaking your demo?
Yeah, that's usually it. You know, yeah, I think pull requests are also just like, the way pull requests set up is kind of annoying. You have to like clone it and then change it on your side and then like do a pull request. I actually did a pull request for this library. A student during my ITP class found that it wasn't reading JPEG files that were JPEG files. So in this case, I just like sent him a pull request, and it was literally like one character of one line of code, and he committed it pretty much overnight. So I think there's definitely like a lot of these people are researchers, so they're also not like heavy like GitHub users. So they're often either they don't take pull requests at all, or they're very happy to take other people's pull requests. It's usually nothing in the middle. It's either like, thank you for helping me with a project that I do out of my own research lab, or I don't take pull requests because I don't know how to use GitHub, or I find pull requests annoying. So this is why I almost inevitably end up forking everyone's work. Like if I find a repo I like, I just end up forking it, and sometimes I use theirs, but oftentimes I'm making tiny little tweaks to mine and just use mine, and then I teach off that. So the ML research world is not the best code friendly environment, but most people are pretty chill with like making updates or edits. Cool. So that's LPIPS. Any questions about that before we jump into clip? All right.
I did have something.
Go for it.
Down 1 second while I think. Okay, yeah, right. So, would this be useful for identifying like adversarial examples and stuff like that?
I mean, In theory, it should be. Yeah, I mean, in theory. So if you're not familiar with an adversarial example is, an adversarial example is an image that maybe to human perception doesn't look like the same image, but like there's some tweak to like the code or like little pixel tweaks here or there that are adversarial examples. And I think that this should, because of how the layers work, it should actually discover adversarial examples. Now, one of the challenges of adversarial examples is it can be model dependent. So this might be an adversarial example for AlexNet or VGG, but that's not the same as saying it's an adversarial example for CLIP or for another generative model. So that's the biggest challenge with adversarial examples is that it can be model dependent. But in theory, this could maybe show some of that.
Cool. No particular experience with it. Just
Yeah, I mean it's a cool idea. I mean that's essentially also why like projection exists, right? Is it's hopefully to find adversarial examples in theory. No one, I don't think it actually works that way, but in theory it could do that. Yeah, but that's a be a cool idea. I'd be really interested to see if people could use this tool to do that.
and so the only way that this tool operates essentially is take 2 images at a time and tell you how different they are. So if you wanted to compare 3 images, you would have to compare all 3 pairs of them.
Yeah, you would probably have to do some sort of averaging example, right? Where you would take like the 2 pairs and then the 1 and 3, and then like average them together or something. It does just work purely off pairs for this, yeah.
Right. Okay. Yeah. I guess there are other techniques for this stuff. Like there's word to vec. I guess there must be image embedding stuff too. And yeah.
Yeah, I mean, embedding in spaces is, I would assume that you could essentially embed this in a space. I assume VGG has some concept of a latent space, and you could probably do it that way. Take the distance score of all 3 of those, yeah. Yeah, I have no idea. I have no experience with that, but I assume it could probably be done. I will say the person who works on this does frequently respond to stuff in Colab. So if you, or sorry, not in GitHub. So if you do have questions about stuff like that, I think the GitHub issues, I think he's fairly responsive in there.
I guess it would be bad manners to ask him, hey, what work has improved upon this? What has made this obsolete since you published it? Hey, maybe there's a diplomatic way to ask that.
Yeah, I mean, he's still active. Like he did, like I said, he did my pull request in like 24 hours, so he's still active in there. So for a research thing that was done in 2018, like he's still interested in it. So yeah,
Thanks.
yeah, of course. Any other questions? Cool. Okay, so let's jump into Clip because I think Clip is a lot of fun. All right, so Clip. So many of you have probably seen Clip and you maybe kind of sort of know how it works, right? There's something about text and something about images. And Clip compares images to captions and provides a score on how likely they match. So this is, again, a scoring system. And I've linked here again to the GitHub repo as well as the blog post. Clip is from a company called OpenAI, which I'll talk a little bit more about in a minute. But this is sort of what Clip does, right? So you provide a caption, or you provide an image, and you provide a caption, and it sort of determines what the closest score is. Now, this thing is like a scoring system where it's trying to rank it compared to other tools. You know, all these models are trying to say they're the best one out there. That's all this thing is saying. But I think it's really interesting because it is text-based, right? So, and what makes Clip different from, say, another like classification model is this is what we call unsupervised, which means you know, there are lots of models out there where you can say, okay, I'm going to show the model 1,000 images of an apple, 1,000 images of a banana, and 1,000 images of a grape, and the model will learn what those are by looking at the category names and the images, and then like figuring out what the network sort of sees there. Clip doesn't really use labels. Clip says, here's a bunch of images, here's a bunch of captions with those images, and you figure out what that means. So Clip is very flexible in the sense that, you know, it can technically work with any data you have, which is really powerful because you don't have to train your own model to do it. So you will hear people refer to Clip as zero shot. What zero shot means is there's no training involved. Few shot would mean a few training samples. So Clip is zero shot. And I realized I did not finish the text on the slide. One of the things to know about OpenAI is specifically a company that is interesting in scaling. like data sets and models. So that means what they do is they will find a model that sort of works well as state of the art, but is trained on small data sets, and they will go out and scrape the entire internet and make the model larger, like add more, like essentially a bigger latent space, or more parameters to it, and then they will train on a really huge data set. So that's essentially what CLIP is. Why CLIP works so well is because it's scraped a lot of the internet. Why CLIP might be bad, and we'll talk about this in a minute, is it has scraped a lot of the shitty parts of the internet, scraped dark parts of Reddit or 4chan. So there's a potential for it being racist or bad, and we should consider that. Now, the way we're probably going to use this tool is we won't have to worry about that, but there are other tools out there that could begin to show bias and other things. So just be aware of that. If you hear anyone talk about OpenAI, OpenAI also did GPT-3 or GPT-2, which you might also be familiar with. Again, GPT-3 is just like this massively scaled language model. That's sort of what OpenAI is known for, is their belief in making the best models is to like find the most data and train it on the most data possible. Oh, here we go. Yeah, so yeah, that's just what they do. So just be aware of that. So we're going to look at an example of this. So I've been making this data set of gemstones or minerals. And what we're going to use CLIP to do is we're going to use CLIP to try to figure out which of my data I should keep and which I should throw out. So here are some examples of the images I have. And knowing how StyleGAN works, what I want to do is I want more images like this, and this, where they're just like single like crystals on a solidish background. And what I want to probably throw out are images with hands, bodies, text. Maybe we'll look at cropped images, those sort of things. The reason I want to do this is that I know hands with a limited data set in a like diverse set look pretty monstrous pretty soon. So what I would love to focus on for this is just getting crystals and just being able to interpolate between those. Now this would be, you know, okay, let's say I have 1,000 images, right? It's probably easier for me to go through 1,000 images one by one and just like delete the ones I don't want. But in this case, I actually had 10,000 images. Actually had 20,000 images because I just scraped a ton of sites. And I was like, I don't really want to go through 20,000 images by hand. So can I use CLIP, which is this sort of flexible captioning system? Can I use that to actually begin to sort my data? So that's what we're going to look at in this example. So there's a couple things to learn as you sort of walk through this process. So CLIP has been out for about 5 or 6 months now. And one of the things I've learned from a lot of people who are using CLIP pretty heavily is the way in which you write a piece of text matters a lot. So we'll look at an example or two of this in when we actually run through the Colab notebook. But the way you structure your captions is really important. So as we go through this, what I might recommend is that first, don't try to just dump it on the 20,000 images immediately. Like pull aside a small data set of this. So we're actually going to operate on like 10 images to start with. Try to like, you know, get the caption or like the sort of the text you're using, like try to like parameterize that to work with your small data set, and then run on the bigger data set. Because I find if you just like start big and like just throw some text at it, you'll get lots of false positives. And I've sort of been toying with this idea of like explicitly filtering your data set. So in this case, what we'll look at is I want images that are just crystals with no hands versus crystals. And then I will say crystals with text or like text in the image or no text in the image. So sort of a binary pattern to begin to filter these. I've got a bunch of examples in the notebook, and we'll walk through a bunch of them just to sort of see how it goes. But I generally find to start with, it's a little bit easier to wrap your head around like binary categorizations, with or without, or with or with not. And then you might want to go into like multi-layered categories. You've got like crystals that are cropped, crystals that are uncropped, crystals that are uncropped without hands, like sort of this sort of thing. So we'll look at this in just a minute. And then I would say like you'll want to play around with a lot with this notebook, just sort of like get a feel for like how, again, I find that so much of working with machine learning is learning how the machine wants to work and then working either against or with that grain. And I would also say like, I find that no matter what I do, I get a lot of false positives, or I get a decent amount of false positives with CLIP. So if you're working with 1,000 images, you might just want to do it by hand, or you might want to play with CLIP, but then also go back and double check. If you're playing with lots of data, losing a little bit, like losing a couple % of your data probably isn't the end of the world, but it just depends on how big your data set is. So we'll look at this in just a minute, but the way Clip works is it provides a score. So it'll provide you always have to feed it 2 captions in this particular example, and it will give you a score of which one it thinks is more likely. And then we'll also spit out just sort of like what the categorization is. These are some examples of maybe, I don't really want to say false positives, but just some interesting things about Clip. So I decided that I would try something like a beautiful photograph of a gemstone or an ugly photograph of a gemstone. And I would assume like, okay, an ugly one is going to be pixelated or blurry or something else. And instead I got a brown crystal is ugly and a blue crystal is beautiful. I won't try to read into that too much, but I think it's interesting that Clip does decide that some images are ugly and some images are pretty. I've got some examples here of multiple gemstones. I was thinking that was more like a grid of gemstone images, and instead it sort of said, look, this looks like 2 gemstones merged together, or I don't even know what this sees in here that is like multiples. But you will see that the confidence score of this is pretty high. So again, there's some weird stuff going on in these models, and we only kind of sort of know what's going on because you're so massive. I also added a caption of a photo of a gemstone with a visible hand. So I was thinking that it was like a visible hand, like you see it. And I think there's sort of like a metaphor here of like the visible hand is craft. Someone visibly like hand crafted these things. So again, remember these are trained on captions and images, and captions are not always explicit. Captions are sometimes, metaphorical or just like, poetic. So Clip will sometimes figure stuff out metaphorically or artistically. In this case, I was fine with it saying like these shouldn't be included in my data set because it's actually kind of right, but like the way it got there is weird. So, this is the fun of Clip. It's a very strange data set or a very strange model, and like some stuff works really well and some stuff works really poorly, and you just kind of have to work your way through it to figure out what's what. There are some other cool Clip tools. I won't go through these, but there's one for natural language search. This does, it searches Unsplash based on text descriptions you give it, and it can also do YouTube video searches. So it uses Clip to actually search through videos. So some really interesting stuff going on in here. I just briefly skimmed how this notebook works, but it's pretty interesting. Many of you are probably familiar with Ryan Murdoch and his Clip image generators. He has a ton of them. They're really cool. Ryan also recently released an image to text generator, which he's not made public yet because he's trying to sort out like how biased it is. But if you sign up for his Patreon, you can get access to it. I think his Patreon's like $5 a month or something. So if you are interested in playing with this more, he also gives you access then to his Discord, and his Discord has all sorts of interesting coding guys who are really like, and I say guys because a lot of them are guys, unfortunately. I will say a lot of coding people in there who are like making really interesting tools, like either taking Ryan's work and doing other things with it or doing other things. But there's some really interesting people in there. They're all actually fairly pretty nice, I would say. I think Grant, you said you've been involved in there, and they're all very smart, and that Discord moves at like a mile a minute. So,
the least nice person there is Tarzan.
What's that?
I'm the meanest person there.
Okay. Yeah. You seem pretty nice, so I think we're fine. You have that nice Canadian. You at least apologize after being mean, so. So there's a ton of stuff going on with Clip, and like I feel like every day people are learning new things about the best practices with Clip. So keep an eye on these sort of things and see what's what. But for now, let's play with this notebook and just sort of see what we can make. I took some of this. This is from there's a company called RoboFlow that does a lot with natural language and computer vision, and I sort of like hacked and modified this code to work with that. So we can take a look at this, and I'll show you some examples of what I played with. I think there's probably far more that's available to play with in this thing, but I think there's some cool tools or things that I've sort of learned just playing with this. So first off, let's check to see what GPU we got. Oh, and let me drop this link in for people as well. Okay, so see what GPU we had. Ah, nice. We still got V100. So one thing to know about Clip is it requires like the latest version of a bunch of libraries. So this is a tool that this will just like load in the latest version of PyTorch. This does take a little bit of time to run. At the very end, it actually restarts the notebook. So you'll get an error message that'll say like, oh, this had to restart. That's fine. That's expected for this notebook. So don't be afraid if you see like, I got some error that like my notebook crashed, what happened? That's supposed to happen with this particular notebook. So while this gets set up, I'm just going to walk us through what's happening here under the hood. So once we've got the latest version of PyTorch, which can take a little bit of time, I really hope that these times are not correct. We'll see. So we're going to load in the latest version of PyTorch up here. We're then going to load in, we're going to clone down Git or the clip GitHub repo. And then we're just going to see, so there's a bunch of available models. Clip comes with a bunch of pre-trained models. We're actually just going to use their default, which is the VIT. It's a vision and transformer model. So we're just going to use that by default. So we can actually skip this cell. So next you'll need to bring in a data set. So again, you can either upload a bunch of images directly to Colab, you can sync your Google Drive account, or in this case, what I'm going to do is I'm just going to bring in those 10 images that I showed in the deck before. I'm just going to import those using GDown. So we'll just go ahead and run this. That'll just import a zip file. It'll unzip it, and then we'll move into the clip folder. Oh no, this is going to be really slow. All right, fingers crossed. We'll see how long this actually takes. I should have done this during break. My fault. So again, the way that these models work is that they essentially do captions, and then they score based on the captions. So in every one of these cells, what we're going to do is we're going to assign both some images, or maybe a single image, or maybe a folder of images, and then we're going to assign captions. And these captions are things that we're going to sort of make up as we go through it, right? So I know that one of the things I want to do is I want to be able to sort based on photos that have text in them or photos that don't have text in them. And this is where I get into like what we call prompt engineering, which is like, how do you write this sentence, or what do you write here? A common thing that you will see a lot of people do with clip is they will say a photo of, or a photograph of. For whatever reason, this gets to like these adversarial examples. If you just write in a piece of, like, just say like gemstone, there's a weird adversarial example in clip where if you were to write gemstone on a piece of paper, photograph it, if you said gemstone, it would find that positively because it knows how to read text. It's kind of crazy. It knows how to read text. So usually what you'll see people do is they'll say a photo of, that way we don't get that adversarial example. So pretty much every example that I have here, I will say a photo of something or a photograph of something. Now here's where it gets tricky is a photo containing text for me scored more likely or like better for my data set than a photo with text or a photo overlaid with text. Like how you write these things matters, which is really annoying, but is also really interesting. And this is where you will lose a lot of time. You'll try to tweak little bits of pieces of words here and there, and you'll sort of see what your data set gets. So yeah, Naoko, that article is really great. So this is one of the challenges of using clip is like, it can just be really hard to figure out like, what do I need to say here to get this to run correctly? God, this is running so slow. Okay. I'm going to keep walking us through, and then I'll quickly run through these notebooks. Yeah, so like the upside of this is like if someone does a drawing or a painting of a gemstone, maybe a photo of a gemstone will also like remove the image of the painting or drawing. So, you know, again, it's like how specific do you want to be here, and how loose do you want to be here? And that case of like those examples of like containing a hand or like with a hand, like it took it sort of metaphorically. So it's like a photo of a gemstone and a photo of a hand, or a photo of a gemstone and no photo of a hand. Like there's different ways to write these things. And which you'll just sort of end up playing with this until you feel like in your small little subset, it's right. And then like you'll sort of apply it to the big data set. You'll still get some false positives, but like you'll maybe sort of start to learn how clip wants to be moved in a certain direction. So this is just an example of how we write captions. So you'll see in the cells, you'll see something that says captions equals. So down here, we've got a captions equals, and it will say a photograph of a single gemstone or a photograph of multiple gemstones. would say a photograph of a gemstone or a photograph of a gemstone with a hand. So once we're loaded up here, I'll run this example. This particular example looks at a single image. So maybe you just want to play with your prompt engineering with just a single image and just sort of like, okay, I've got this image and I want to see which one it matches up with. So did I say gemstone? Gemstones, perfect. Maybe we'll find a gremlin and a gemstone. So you'll point this at an image. So you'll just put in the image path. And from here, you don't really need to do anything else. The way that I've sort of written these notebooks is all of your import functions are the cells, all the import functions go at the top. Imports are just importing library code, a library of code, a code library. There's different packages that come with Python. Ignore this. Anything we see imports, you most likely will never touch that, or you'll be adding to it, and I'll tell you when to add stuff to it. There might be a definition of a function, and then right after that, I will have all of the cells you want to edit. So basically, you'll see these things and you'll be like, that looks like a path, that looks like a caption, edit those. And if you aren't interested in code, you can just skip everything else because all these cells should run as is. How are we doing on loading this? God, my internet must be terrible today. All right, well, we'll keep going. I'll walk through these and then I'll quickly run some examples and we can sort of look at them. And also, if you want to jump into co-working sessions, like these are also like good things to explore together during co-working. So this is single image scoring. This will just look at a single image and apply A or B. And what you will get is you will get a score that looks like this. So if you look here, what will be spit out is the image that it looked at. There will be a score. So this score is a percentage, and this will always be your first caption, and this will be your second caption. Now you can add multiple captions. You can have as many captions as you want, in which case you'll just get different scores. These scores will always add up to 1. So you can think of this as the confidence of the model. How confident is it that this is the caption that it matches with? So in this case, this was, I believe, beautiful photographs and ugly photographs of gemstones. In this case, it said with 87% confidence that this was a beautiful photograph of a gemstone. And that meant that 12% it was like, maybe this is ugly. In this example, you'll see that it said with 60% confidence, give or take, this was an ugly photograph. And with 40% confidence, this was a beautiful photograph. So your confidence score actually helps you also understand how confident a model is. So in this case, like this is a pretty low confidence score. If you said 50-50, I think this is like, or 51-49, I think this is ugly versus beautiful. That tells me that like the model isn't really sure. So you can kind of use these confidence scores to also see how well your prompt is applying. In the case of ugly and beautiful, like, God, who knows? That's like, I don't know, that's like such a silly question. But it's one that people almost immediately ask Clip because they want to know if Clip knows about beauty. And it's like, Clip doesn't know anything about beauty. It just knows about what it's been given as data, which means, all right, my political statement here is, I kind of believe that it might just assume anything brown is ugly. And you can take that however you want. It could mean that it's been trained on mud and it finds mud ugly, or people just have a bias against brown things, maybe brown people. So, you know, be careful using stuff like this, especially on people's faces. You'll see I purposely avoid trying to give Clip people's faces. You're welcome to try it. Just, you know, be careful about what you do and what you share. And definitely be careful about implying that the machine assumes black people are ugly or whatever. You'll get yourself in very dangerous and very scary positions very quickly by making proclamations like that. But again, this data set is probably trained on a bunch of bad stuff, and therefore we get into weird places. All that aside, what's important here is the confidence and your caption. So this is an example of just a single caption. Let's see if we are finally running here. Oh, maybe almost. Okay, we're almost there. So that's the single image. What we can then look at is this will just provide a score. This won't do any sorting for us. The next cell here will do sorting. So in this case, what you will feed in is a path to a folder. So what I recommend doing for this one is feeding the folder path to this part and leaving the asterisk dot asterisk. This is basically saying if you're aware of, there's sometimes what we call invisible files in folders. This will skip invisible files. Invisible files will likely crash the system. So all this does is say, like, look for anything that's named something dot something in a folder. So just update the folder path, but leave this here. And then we've got our captions here below, right? So we've got a gemstone, a photograph of a gemstone, or a photograph of a gemstone held by a human hand. I think I decided human actually like kind of confused it. And I think I said, where did I end up with this? I tried a bunch of different things to get this to work. And I think I said, comma contains a hand. So again, like these are such weird phrasings. Like I wouldn't see a human writing this phrase, but maybe they did, and that influenced my data set here. So let's see, did we get our data pulled down?
Did a robot write this?
Well, I would also say like it's probably very likely that the robot did write some of these captions. You know, again, data scientists, especially at a company like OpenAI, are very lazy. They don't want to go through a million images and write captions by hand. That would even cost you a lot of money on something like Mechanical Turk, right? At a cent an image, that's still a lot of money. So, you know, they don't want to do that either. So they probably get a robot to write some captions for them, which is its own issue. Okay, so now I've got my data set here. I've got it loaded, right? Oh, I didn't pull in clip. Okay. Okay, so I've pulled down my data, my zip file of images. I've unzipped it, and then I've made sure I imported clip. So one thing I should have noted here, you have to run this cell, let it crash, and once it crashes, then you run the other cells. Because if it crashes, it won't run those cells by default. So now we can just let's run this really quickly. So let's actually take this caption down here. Sorry, I know I'm scrolling around a little bit fast. So let's take this caption. Let's just run this on one image. So let's, oops, a photograph of a gemstone. So let's find our image that has a hand. There we go. So let's see. I think it's saying this image. All right. Okay, so this image has a hand. What's interesting about this image is the hand is gloved. So it's also like, can it find that? So let's grab this path. And let's put this path in here. And let's run this. So the first time you run this, you'll need to download this model. So it's going to download this model, which is called VIT-B/32. I believe this is Vision and Transformer something something. And so pretty quickly, it will spit out an image that says, a photograph of a gemstone contains a hand. So what this does is, here's my confidence score. This confidence score aligns with these captions in this order. So order matters here. And it says 73% confidence this is a photograph of a gemstone that contains a hand. So if we tweak this a little bit here, like let's say a photograph of a gemstone with a human hand. Let's see if we get a positive result there. Yep, so actually it's more positive this time. So maybe we want to keep a human hand, I don't know. Let's say a photograph of a gemstone held by a hand. So now my score dropped a little bit. So again, this is on a single image, right? So you don't want to tweak it too close to a single image. You might actually want to run this on a small set of images and just sort of see how it produces. So if you do want to do that, what you could do here is, well, actually, let's take a look at this down here, because that's essentially what this does. So this is going to, so let's take that same image, or the same captions we have here. Also, let's take that caption, and we'll swap that out in here. So this is going to say, go through all of the images inside of this folder, which is this folder. So go through all of these files and then compare them to these captions. And what it will do is at the end, Oh, so then what you also want to do is if you do want to sort these into folders, what you'll want to do is you'll want to provide it a place to save them. So let's do this. Let's just make a new folder here, and we'll call it tests. And we'll copy that path. And we'll just say, let's save these to this folder. So what it's going to do is going to make two folders, one labeled with this caption and one labeled this caption. And what it thinks, it's going to put those images in those folders based on that. And this will only do whatever, like, it's just going to be basically like if it's 51% or higher, it's going to stick it in that folder. So we'll go ahead and run this cell. What happened here? Oh, sorry, I know what happened here. This is not the right path. I actually need to just grab this path. Because of how I unzipped this and downloaded it previously, there's actually two content folders. Very confusing, but this is what I want to do here. Slash, damn, typos today. Okay, so now it's going through my entire data set of my 10 images here, and it's going to score each one of them. Now I tend to find the first one goes slowly, and then after that it happens pretty quickly. So we'll see how long this takes to run. Yep, so now it's just running through all these. And it's sharing scores for each one of them. So, okay, so let's see. So photograph of a gemstone held by a hand, 76%, looking good. 82%, also good. The photograph of a gemstone, that's correct. The photograph of a gemstone, correct. Gemstone. So here's a case where it just found a photograph, even though this is a painting, but you'll see the confidence score dipped a little bit. Now, my guess is that if I added a third category that was, say, a painting or a drawing of a gemstone, this one might actually score that higher. I don't know. We'll see. We could try this. Photograph, photograph, photograph held by a hand, and a photograph of a gemstone. So this one scored really accurately. Now this is on 10 images. With 1,000 images, I might get a couple false positives. And if I come over here into tests, you'll see I've got two folders. One thing that you'll note is it changes spaces to underscores just for my own sanity. And inside those folders are just the images. So in this small sample, it worked pretty well. Now, here's the challenge here is that in one of these, this is correct, right? It's a photo of a gemstone, but it's also got text in it. So maybe now I want to take this folder. So let's take this folder and let's look at this folder's path. And let's just say a photograph of a gemstone without text and a photograph of a gemstone containing text. So I don't really know if these scores are going to work or if these like prompts are going to be correct, but let's just run this and see what happens. All right, so here we got our first false positive, right? So a photograph of a gemstone without text. This was essentially a false positive, but if you look at the score, it wasn't really that confident in this. So this tells me that it's kind of knows that there's text here, but my guess is that sometimes what I find happens is it assumes gemstone without text. So it's sort of like grouping these things in an interesting way. I've sort of like, in just playing with this for a day or two, I sort of found that this was a common thing that happened. So what you might want to say is a photo of a gemstone. So here's a issue where like I've got two folders now that are sort of the same name. So maybe let's create a new folder called test2. And then we'll dump stuff in new folders. This is pretty hacky, but it's fine for this sort of setting. So we'll say a photograph or a photograph of a gemstone without text. So that way it's not even looking for the word text. It's just sort of like saying this is just a photograph of a gemstone, and then a photograph of a gemstone containing text. So let's run this and see if this changes our results. Yep. So this was already better. So sometimes what happens is you don't even want the word in there, right? If the word is in there, I don't know if you guys have ever played with language models, but just having the word in there, like sort of saves it as a position. Yeah, text within a gemstone, text within a photograph. Yeah, this like makes your brain kind of hurt, like trying to think about like how it's conceptualizing words. But sometimes just not having the word in your phrase, even if there's no not before it or without or like whatever, just removing that word helps the model actually quite a lot. And you'll see here the confidence score is so much better, right? Before we were like 40-60, now we're 80-20. So prompt engineering is like the key to CLIP, and it's like kind of annoying because as you add new categories, you want to sort of slice and dice more and more, and it gets harder and harder. But this is sort of where CLIP is really powerful because, God, to train this with like hands, text, like you have to go through and like create your own data set first of all those supervised data sets, and then you have to train a model, and you have to like check to make sure the model's right, and then you have to like actually run it on your test data set. So like this is way more flexible and way more interesting, but there's still challenges here. Writing these prompts are a little bit annoying. So I've got some other examples here. I think we can wrap it up for the night. If you want to go through these examples either in co-working or just by themselves, you can. This example uses a max probability. So sort of similar to what we do with LPIPS. We're basically going to say like, if you're not really confident about this, please don't put this image anywhere. So this will basically say there is a, where is my max score here? Oh, sorry, this does a thing. This does something different. This, no, this is not right. I had an example here that this would take a score. Oh, sorry. So this is multiple classes. So this is if you have more than one class, what it will do is it will still take whatever has the highest probability, and I'll stick it in that class, right? So this is sort of exclusive. Every image has to go in one folder, but you can't have the same folder or the same image in multiple folders. That's what this example does. So you could look at, I think Adam, you and I were talking about this at one time, that you wanted photos on white backgrounds. So you could try a photo of a chair on a black background, a photo of a chair on a white background, a photo of a chair on a, I don't know, some other background. One thing that's hard with this is you can't do like if else, right? You can't say like if on a white, cool, just like put in there. If on a back, like what is the other? The other is always sort of the hard category to choose from. So you do have to do some prompt engineering to sort of get this to figured out. But I think there's some really cool opportunities here. So this will stick. This will pick a single folder to stick in, whatever has the highest probability. This one down here is the one I was thinking we were doing, which is a sort of greedy sorting, which is like, as long as my probability score is above or below a certain number, I will stick it in here. So 0.6 is actually too high. I would say like 0.2. So it'll say, as long as something fits into this category with at least a 20% confidence, stick it in that folder. So that means you could have the same image in multiple folders, which is good for sorting if you want to do like, maybe you want to make multiple data sets. You want to try training on multiple different types of data sets with StyleGAN. This would be like, what's a good example of this? You could have a photograph of a single gemstone. You could have a photograph of a red gemstone, a photograph of a red and green gemstone, and it could try to like combine them. One thing to note is that the more categories you have, probably the lower your probability needs to be, right? Because this all adds up to 1. So if you've got 20 categories and you want it to go into multiple folders, you do kind of want to lower this value a little bit. So you might want to play with this. Again, this is a good thing where if you don't want to save these, if you don't want to save out your images, you can just take out, there's a break here. Actually, let me add a little note here. So this saves out images. If you select all this and hit Command this slash, whatever that one is, that'll comment out all of your code. So if you don't want to save out your images, but you just want to see what the results are, you can just comment that out and that'll just show you the results. So if you're doing some engineering, some prompt engineering, and you just want to sort of like see what results you get as you play with the prompts, you can comment out the save function, and this will pretty much be the same everywhere. So let me just copy this here, and I'll put this here. So basically, like wherever this is, like you can just comment out below there, and it'll just stop saving the images. And then once you've sort of figured out your prompt and you want to run it, you can actually uncomment it, and then actually save out your images. Below here, I was trying this thing really late at night one night where I was trying to determine whether captions, like big groups of captions with like multi-category things could work. Or if it was better to do like this, which was like a bunch of single categories and then trying to like combine each of those individually, whatever. This was like quite insane. If anyone wants to explore this, I'm happy to go through this and through these notes with them. But I actually found that I personally found that this worked better than this. So this was like break these things into smaller groups and then sort by them. I found this personally, which is like just write your labels so that it covers all of your categories better. So this was like, whereas I showed you how to do sort of like the if-else operator and then take that folder and do another if-else, this was sort of like, can you do that all with one caption label? And in general, I found that this worked fairly well, but this requires a lot more prompt engineering because you've got this thing where like this contains a hand, this doesn't contain a hand, and it's like you've got that issue that we just showed with the contains text or doesn't contain text. As soon as you add that word, it kind of looks for it, and then you hope it finds the negation, which can just be a bit of a challenge. So I would really recommend, like for this week, just if you're really interested in playing with this, just play with it. And if you find like, oh, I found that this sort of phrase structure works better, like pop that in the Slack because I think other people are going to find that interesting too. So, you know, there's a lot of sort of, Clip is almost entirely prompt engineering. Even the Ryan Murdoch notebooks where it's sort of like you're making images from text, he does a lot of prompt engineering to make sure that it like does the right thing. His notebooks also, maybe we'll look at this. Actually, there is a notebook to do this for StyleGAN models. So you actually take your StyleGAN model and use Clip to move it. I might try to look at that in this class. I think it'd be fun to look at. But there's a lot of tricks that folks have learned about, like you do the negation separately, or you do other like arithmetic to these tools. But I would say start with this because it's pretty low level, and you can just sort of see like if I change the text to this, how do my probabilities change? Right? There's a little bit of good feedback there of like, okay, if I do this, I get this. If I do this, I get this. So I might just start there and just sort of see what you get for your results in your data set. But I'm really fascinated to see how we can use this as a really flexible tool to begin to sort our data in better ways.
I'm curious how it would work if you remove the shared attribute, because we know all of these, at least in this data set, we know everything's a gemstone. So if we just remove that prompt and look for a photo that contains a hand, a photo that contains text, I'm curious how that performs compared to requesting everything with the gemstone, for example.
No, that's a great point, and that's probably true. I should say that this toy example doesn't have any non-gemstone photos in it, but my real example that I was actually building this for did. So I had some like there were photos of people, like people miners in like mining hats, but no gems. So I did keep the gemstone in there for that purpose. But that's a great point that like in this data set, we probably don't need the gemstone text because there's an assumption that this always has a gemstone in it. So that's a great example. Where this particular data set, we could engineer around that. So that's a great point. Yeah. Cool. So I'm happy to stick around for a couple minutes if people have additional questions. Homework for this week is really just to play with these tools. You know, play with LPIPS, see if you find like a certain range of numbers that you think are interesting. See if you find different tricks that sort of manipulate your data in a certain way, or play with Clip. I'll say like, these are not the cleanest workflows, right? Like you have to upload stuff to Drive, got to make some folders, maybe dump those folders into Drive. Like this isn't the cleanest stuff. So, I know some people in here are interested in making machine learning tools. So if you are interested in like tooling, like how could we like improve this process? The downside of these things is you pretty much need a high powered GPU. And since I can't assume that everyone has a $3,000 GPU in this class, we're using Colab. If you were to go buy your own GPU, it's probably a little bit easier to run these locally. Usually what I will do is I have a Linux machine that I connect everything to. So I'll upload all my data there and just do stuff locally because it's a little bit easier than trying to deal with Colab and moving stuff around. So yeah, there's a lot of places where I think these tools could be improved. I've seen a lot of people making like sort of front end tools for Clip. There's a Clip notebook. I don't think I have it. Let me see if I can open it really quickly. It's in a different account. Here we go. So I covered this in my Colab class, but there is a way to sort of get a front end a little bit in Colab. So there's this app param feature, and then you can give it a type, and it creates this little like it's not the prettiest GUI, but it is a GUI. So you could also look at maybe do we improve that Clip notebook by actually like giving people like a text interface to use. This is an insane list of features. This is like not this is too many features for this sort of GUI, but you create a really simple GUI that just has some like text and things, and that's this app param command. I think there's a video in the Colab class. I'm going to make a note for myself. Link to param Colab demo, where Leah, my co-teacher in that class, did a whole demo on how to build sort of GUIs for Colab. So you might find like a GUI interface a little bit easier for you, or maybe someone wants to have fun and just like learn a little bit of Colab and make this for the class. That's always helpful. I love when people make tools for everyone to utilize. So if you are interested in just learning a little bit of Colab, you might find doing something like that is helpful for the class, or just like to learn a little bit from. Yeah, so there are ways to sort of make these a little bit more friendly for people within Colab, but I'm seeing lots of people starting to make clip tools and that sort of thing, which I think are really interesting. Yeah, this one has not been publicly released, so I can't share this with anyone. But you can still use these parameter features. If anyone wants to stick around, I just heard my doorbell ring and my partner's out here, so let me just go answer that real quick, and I'll be back in just a minute to answer questions. So if you do have questions, stick around, and if you don't, I'll see you next week. Okay. Sorry about that. So what questions do people have? You guys all stuck around thinking someone else would have questions? Go for it. Yeah.
Yeah, I do have a question. So I don't know, this is kind of an obscure question. Over the break I was trying to get LPIPS to run on my laptop. And it is having like all these import errors, and so do you know if Anaconda, the way it works, because I get the sense that all the errors are coming from the LPIPS library that I downloaded.
Yeah, that's a good question. So
Yeah.
did you
So
run
does it like install all the dependencies?
pip install -r requirements.txt when you set up Anaconda?
Yeah.
So I do find that a lot of people often don't actually fill out requirements completely as required. They
Mhm.
often skip certain things like SciPy or other like, well, everyone's got this installed, right? So they usually don't. Um, Also, this one, it looks like it requires, I'm just looking at the instructions here for installation. It looks like it requires PyTorch 1 and Torch Vision, which usually means if you're installing, what kind of laptop are you on?
Linux.
Linux. So, um, and I assume it probably doesn't have a GPU that can use. It doesn't have like an NVIDIA GPU, does it?
It does.
Okay, so if you install PyTorch, it might be able to get away with the GPU version. I also think that
Mm.
sometimes if you install the CPU version, there'll be error messages because these people just assume you're using the GPU version. So
Mhm.
I would say like if you want to send me the error messages, I can take a look. It might be that you want to like just leave an issue in that repo and see if they can figure it out.
Yeah, I don't know. It was just yeah. What I get the sense it's doing is I'm like wondering if somehow the package that I installed for LPIPS is in a different like environment for Anaconda because I have CV installed, but it keeps giving me all these like errors saying that like CV2 functions don't work. So
Uh, Interesting. It does look like I'm looking at the requirements here. It does look like it should install OpenCV, but that's a pretty old version. So I wonder if it needs like a newer version. This is also the challenge of things where like these these tools are often out of date in terms of their requirements. So you might just need to play with updating to the latest version of certain code.
all right, well, I'll play around with it more.
Yeah, just DM me
But
if you still get errors, DM me and I can see if I can debug that.
okay, sounds good. Thanks.
Cool. So I see Grant linked to Ryan Murdoch's Patreon. So definitely like if you want access to some of his tools. So basically the deal is he has some public notebooks that he releases publicly, but he's got some private notebooks that he is basically constantly improving on. And those are, I'll be honest, they're much better. And it's like $5 a month to get access to those, as well as to get access to his Discord, where lots of other people are also making cool notebooks. It's kind of worth it if you're interested in playing with clip stuff. Like Ryan and his cohort are probably like the best people at clip at the moment. So it's definitely worth following him if you've got $5 a month to spare. I did an interview with Ryan. I'll link to it. I did an interview with him last month. He's like a PhD student who also just does this in his spare time. I hate people like that. Um, but very smart guy, very cool, and is like doing a lot of interesting stuff for the community. And I can quickly show. This is again not a public model, so and this video won't go public until he's released it. I don't think so. I can also show you just sort of what he's got another model or another notebook that he has started. This one. Let me share my screen real quick. So I'll demo this for you. This is not public, so but also like you can pay him and get access to the notebook if you want. He's got a notebook here that will provide captions or provide text based on the image you upload to it. So it's almost like a classifier, but it's really flexible in a really interesting way. And let's see, this is probably going to take forever to run. So let me just see if this works. But essentially what you do is you upload an image. I've been sharing examples of this on my Twitter feed actually, so maybe we can just do this here and just show you what it outputs to. Where basically you upload images and got a media here, profile, media, and it returns tokens. We call these tokens because that's just how what they're named inside of clip. It'll return words that it thinks define the image. So I uploaded this image that was like it's like an old like 19th century like Art Nouveau like pattern or something. And its first guesses were that it came from Redbubble, which I think is really interesting because that probably means that someone just uploaded that image to like a like pillow or something and like was trying to sell it through Redbubble. Um, I think this also kind of shows you a little bit about what Clip has been trained on. If it sees an image and it's like, oh, that looks like an image that would be uploaded to Redbubble, they can kind of tell you that it's been trained on Redbubble. You will also find Twitter on there a lot. You will find, I found Visco, which is like a camera app. I found Visco on there. I found Unsplash on there. So it's clear that one of the things they did is they scraped a bunch of public open access image stock websites and then grabbed the captions from those and trained on that data. So like one of the interesting things about this is you can start to see like it gives away what it was trained on. So there's some really interesting results in here. This was like also, you train these for a little bit long. Like the longer you train them, the better the text results get. This was a very early example of one of the things I was training on. I also got some other examples. Let's see, so here's one. So this was, it said like, oh, this looks like an image that came from Unsplash. And it literally, the image I used came from Unsplash. So it has definitely been trained on the same things that I've been using. Visco shows up because it has that Visco colorization, that sort of like, well, actually it was, here, I can show you what image it was. It was this image. So, feeding that through the model, it was sort of like, this looks like an image from Unsplash. And yep, it was. Also, it's got the color grading of Visco. And yes, it does. So this is one of the things that like isn't text generation, but I think it helps you understand what the model sees or what it's been trained on, right? So it knows about overpasses. But the thing is, this image isn't really an overpass, right? But it probably doesn't know like brutalist architecture, abstract architecture, right? Like it might, but like it doesn't really think about it in that way. So, using all these tools, it's sort of like you have to learn how the machine thinks so that you can then operate with that. And all these tools are sort of like, this is what Ryan's bread and butter is like, he just spent the past 6 months working purely in Clip, right? So this is a StyleGAN class, but Ryan could probably teach a Clip class that would be like way better than anything I could. But using all these tools, you can begin to understand what the model sees. You can begin to sort of like pull out all the details of these things and begin to play with those. So what I've started doing over the past couple of days, a thing that I did, which I think is kind of fun, is I will use Ryan's notebook to figure out what the terms are. And then I will use this other notebook that is private, but is written by a couple of folks from that Discord, Class Spectanon being one of the main people. So I'll use those images to then tweak the uploaded image. So I tweak this image using these text pieces, and it begins to sort of like almost like double down or like really emphasize those things. Like if you ever used Deep Dream before, this works like Deep Dream, right? It takes the image and it like sort of overemphasizes the things you tell it to. So this is doing that. And then basically like you can eventually get these fun little videos of the training process. So this is taking that image and it just sort of like begins to like optimize toward it. And so what I think is kind of cool about this is it's using like its own self-ordering sort of system, right? It says like, in this image, I see these things. Now let me like hyper optimize toward that. And I just think that's a really interesting way to think about like, I don't like autonomous AI art, but like this is kind of autonomous AI art because it's like using whatever it sees and then optimizing toward that. So I think Clip is a really interesting tool. There's so much power in it because of this flexibility in it. That people are doing all sorts of fun and weird things with it. So yeah, there's a couple notebooks Ryan has released publicly that allow you to do this, but all the ones in the Patreon and Discord are way better. So consider this like my plug for Ryan's Patreon, and I guess you can help pay for some of his PhD, which is never a bad thing. So yeah, so there's a lot of cool tools with Clip. I'll say another thing, the Discord has a lot of people doing lots of cool stuff with it that I cannot follow because they are like postdoc kids who are like, I guess they just post in the Discord all day. So like I'll come and check it out at night and there'll be like 50 new messages of people solving new things. It's really cool and really fun, but it can also be really overwhelming. So just heads up on that. But yeah, I think there's lots of cool stuff going on in there in Clip. Cool. Yeah. So unless there aren't more questions, I will wrap up for the night, and then so you can expect an email from me or like a calendar invite from me over the next day or two for our 2 co-working sessions. So those will be every week. I think we'll stick with those times unless I hear from people that like, oh, this really isn't working for me. Could we do a different time? So for here on out, you can sort of assume that Saturdays and Mondays we'll have co-working sessions. And again, those are optional to attend. If you have something going on Saturday at 2 and you don't have anything pressing to talk about, you don't feel like you need to show up. If people want, we can record those sessions. Sometimes people feel uncomfortable if I record those because they have questions specific to their projects. So I might just play it by ear and see if people are cool with me recording those. And that way people can have access to the answers or whatever I do during them. And if not, we'll go from there. So yeah, so I'll post more on that this week, and I'll leave notes for people. Sound good? Cool. All right. So if I don't see you in a co-working session, I'll see you next week then. All right. Cool. Bye, everybody.